This video is for Math 116, and this will get us started on Chapter 2. And so in Chapter 2, we're going to talk about circles and parabolas. So the first section is kind of split into two pieces, and it's mostly about the equation of a circle. So a circle, if you go back and, the Greeks, so let me back up for a minute and talk about the conic sections. It's kind of interesting, and it also illustrates something that was typical of those ancient civilizations. So if you take this figure, these two cones that are connected at their tips, okay, now where that figure comes from is, I think, part of the interesting thing about this, but I'll talk about that more in a minute. If you take this figure of these two cones tip to tip, and you slice it parallel to the base, right? Then you get a circle, okay? If you slice it at an angle to the base, then you get something called an ellipse, which is basically an oval. Ellipse. And in fact, the path that the planets, or at least the path that the Earth follows around the Sun, is an elliptical orbit. It's a slightly deformed circle. It's not perfectly circular, and that bothered astronomers for years until they figured out through the calculations of Kepler and Copernicus and Tycho Brahe were all collecting this information in the 1500s, I think it was, and they determined that it's an elliptical orbit. It's more of an oval rather than a perfect circle. Okay, what else? Oh, if we come in here along the edge and slice it like this, okay, then we get what's called a parabola, all right? Now we're going to focus on the circle and the parabola, but we also have the ellipse, and then the hyperbola is what happens if you slice it like this so that you get two pieces. You get one piece here and then one piece there. Okay, your typical or your classic hyperbola comes from the rational function 1 over x. Okay, and there are many other versions of that hyperbolic function. So these are what the Greeks called conic sections, because they came from these two cones tip to tip, slicing it in different ways. Now, I've done a little bit of research on, the Greek conception of the conic sections, and so I, of course, was, curious, well, where did they get these two cones tip to tip that they're getting all these shapes from? It was a gift from the gods. Very much like a lot of other things, when you go back to their basis in Greek's culture, something like the lute, where did the idea for that stringed instrument come from? It was a gift from the gods. So a lot of these things are, really, it's interesting, and I find it a little frustrating to try to find out more about this and to always have it end up as just being a gift from the gods. But that's what happens when you try to go back to the origins of some of these important ideas. Okay. So we're going to talk about circles today. And again, if you go back to the way that the Greeks conceptualized the circle, it was what they use this term, a locus of points, a collection of points that are all equidistant from the same point, that being the center of the circle. Okay, so that's the defining feature of the circle, is that you've got this constant radius where this distance is always the same for any point xy on the edge of a circle is always going to be the same distance d, or I'll replace that with an r since we call it the radius, same distance r from the center of the circle, any one of these points is always going to be that same distance. So we can go back to our old friend, the distance formula, right? That says d is the square root of of x2 minus x1 all squared, y2 minus y1 all squared. And so we replace this with r is equal to the square root of x minus h all squared plus y minus k all squared. And then if we square both sides, this is the form, the standard form for the equation of a circle. Okay? You've got the center of the circle as the point hk. They show up here and here. And then the value of the radius will show up over there as the square root of whatever that number is. Okay, so there's the standard equation. Let me write that over on the side to open up some space on the board to look at examples here. So our equation says r squared is x minus h all squared plus y minus k all squared. All right, so okay, so these problems are on page 75. It says determine the center of the radius for each circle and then sketch a graph. Okay, so problem 2, we've got x plus 4 all squared plus y plus 2 all squared equals 16. Now notice that these are subtraction symbols in the standard equation. And so if you see a plus here, then that means what you're working with is x minus negative 4. And over here, y minus negative 2. And so the coordinates for the center of the circle are negative. They're negative 4, negative 2. And our radius here is the square root of 16, which is 4. Okay, so if we want to sketch a graph here, okay, negative 4, negative 2 is right there. And then we want a radius equal to 4, so that would put it here, here, down here, and then, let's see here, 1, 2, 3, 4, yeah, about over there. My circle's a little bit, I mean, if it's much better if you have a piece of graph paper, then you can get a better sketch on here. Okay, my sketch is a little sketchy. Okay, so that's problem 2. Let's keep working on these, and then we'll look at the next section where the problems get a little bit harder. Okay, problem 4. We've got x minus 2 all squared plus y plus 5 all squared equals 27. All right, so the coordinates for the center are going to have the opposite sign to what's inside these parentheses. So the x will be positive 2, the y will be negative 5, and our radius is going to be square root 27. We can get a good approximation for that. It's going to be what? It's going to be 5 point something, right? Because 5 squared is 25, so yeah, 5.2 is a pretty good approximation. Let's see if I can do a better job on sketching the circle. All right, so 2, negative 5 is the center of the circle, and then the radius is 5.2. So it's going to look a little bit like that. Well, I'm happier with that circle. It's still not great, but what we really need is a good grid to sketch these graphs on. Okay? And so I encourage you to get some graph paper. I'll try to remember, I've got printable graph paper that you can download and print out, and I'll try to remember to post that with this assignment. Problem 6. See here, x minus 5 all squared, or y minus 3 all squared equals 50. Okay, so the center for this circle is the point 5,3, and our radius is square root 50. which is going to be just a little bit more than 7, right? Because 7 squared is 49. So this is going to be about 7.1. Okay? And so what is that going to look like? All right, let's see what we've got here. 5, 3 is the center. So that's going to it's going to go up to 10, and then over to 12, and then down to -4, and then out to -2. And then it'll look something like that. Okay. All right, so those are the first couple problems going from the equation to the information and the graph. All right. Now, the next couple of problems, we're going to start with a graph, and we're going to go back and try to identify the center and the radius, and then write an equation for it. So let's do that. Problem 8. Let's see what we've got here. We've got a point there. And let's see, the circle looks something like this. This is the point 4, 6. Over here, -8, 6. This should be a diameter. Yeah, each line represents a diameter. That means the center of that circle is exactly halfway between these two. So if we take the average of -8 and 4, that should identify this point as -2, 6. And I think that matches up with what we see on the scale in the graph. Okay, all right, so now we've got the center of the circle. Our radius here has got to be 6, right? The distance from -2 out to 4 is also the distance from -2 out to -8. That's a distance of 6. So now we've got all the information we need, so we can write the equation. X plus 2 all squared, y minus 6 all squared equals 36. Okay, let's see here. One more problem in this very first part of chapter 2. And so we'll take a look at problem 10. So what do we have here? We've got a little circle right about there. -5, -2 is here. And -9, -2 is over there. Okay, so again, the center of the circle is got to be halfway between them. You can also say to yourself, well, the total distance between -9 and -5 that's a distance of 4, which makes the radius equal to 2. All right, that's another way to do this. And so the distance from -5 would put that at -7, -2, and then this is a distance of 2 as well. So now we've got the center and the radius, so we could call this x plus 7 all squared plus y plus 2 all squared equals 4, right? The radius squared. Okay, those are the basic ideas for the equation of a circle. Now in this second half of section 2.1, we introduce a new idea called completing the square. You may have seen this process before in another class, but it's a standard idea where you've got something. Well, first off, let me write down some perfect squares here. I'll do it up here. And this is in the textbook. X plus 3 squared means x plus 3 times itself, and that's x squared plus 6x plus 9. Okay? I'll put up x plus 4 squared, and that'll be x squared plus 8x plus 16. And then I'll put up one more. And I'll just refer to these to try to illustrate what I'm talking about when I go over completing the square. Okay? So let's say we had something like x squared plus 14 14x, I'll leave a space there, equals 2. And this is actually a process, this process is probably one of the deepest ones in mathematics. I mean, this is where the quadratic formula comes from. This is how the Arabs and I think the Mesopotamians too, but to a lesser extent. But the Arab process for solving quadratic equations, which was eventually passed into Europe in the 12th century by a mathematician named Fibonacci, also used completing the square. So the idea here is that we want to rewrite this. So the problem is that we've got two pieces that have x in them, and we can't combine them together because they're not like terms, right? The process, if you've got, 2x plus 5 equals 9, you get the x by itself, right? And then you get x equals 2. Excellent. Okay? Here we can't get the x by itself because we've got both an x squared and an x. So the trick is to rewrite this as a perfect square and then square root it so we just come out with that single x. See here, you've got an x and an x squared, but if you go back to this form and then square root it, you've just got the x and you can pull that out. Okay? So the question is, well, what is this as a perfect square? X plus what squared? Okay? Well, so this is where we look at our examples. Here's the so you've got this middle number, okay? In the quadratic formula, we use the letter B to represent that. So you've got this middle number. Where is it coming from? What's its relationship to the number that's inside the parentheses, right? If you know the 10, where does the 5 come from? If you have the 8, how do you get the 4? What's the relationship between the 6 and the 3? And the answer to all of those questions is that what's inside the parentheses is always half the value that you're going to get as that second coefficient there. Okay? So take half that and plug it in there, and there we go. Now, this is fine. These things are all equal to each other. Here, I've just done something kind of fishy because this and this are not actually equal to each other, right? This is not equal to x plus 7 squared. X plus 7 squared is x squared plus 14x plus 49. So this is the key to completing the square, is to figure out what this number needs to be and then to provide its square, okay? So now that we know the 5, square it to get the 25. If you know the 4, when you square it, you get 16. So what we're missing is a 49, and I can't just write it in there because I want it to be there, but I can always add it to both sides. That's one of the classic techniques of algebra. Okay, so now this thing is equivalent to x plus 7 squared. Over here, we get 51. Okay, so back in the day, when people used completing the square to solve their quadratic equations, the next step would be to square root both sides, and you would get x plus 7 is plus or minus square root 51. And so the answer to this equation, or the solutions for this equation, are going to be -7 plus or minus square root 51. Okay. So that's the idea of completing the square. So now we're going to apply this to these equations of circles, right? So this is the standard equation, that's the standard form, but we don't always get the equation in standard form. So let's look at some examples of those. These problems are on page 80. And, all right, let's see here. Problem 2, well, I'll go ahead and go over these first couple problems as well. There's something different in these. X squared, y minus 1 squared equals 1. So you can see the y coordinate for the center of the circle is going to be 1. The x doesn't have anything, right? So that just means that the x coordinate is 0. All right? And then our radius is going to be square root 1, which is 1. Okay, let's see here. Find the center and radius. Just checking to see. I don't need to sketch that graph. But we will need to complete the square once we get past problem 4. So this is something that shows up from time to time when you're working with these problems, is that you might have coefficients in front of these parentheses. If that's the case, divide, well, let's do it this way. Divide on both sides by 3. Divide everything in the equation through by 3. These cancel out. This becomes a 2, and we get x plus 1 squared plus y minus 1 all squared. Now you might be thinking to yourself, well, what if these numbers aren't the same? What if those 3's, what if it wasn't 3 and 3? What if it was like 3 and 4 or something? What would happen then? Then it's not a circle, okay? That's actually one of the interesting things about these conic sections, is that if you've got this equation, if these are the same number, then you've got a circle. If they're different numbers and this is still a plus between them, then it'll make an ellipse. If you've got, whether it's really, I think it's the same or different numbers, then you're going to have that hyperbola. Okay? And the parabola is a situation where one of these is squared and the other one is not. But we'll get to that. Okay? Alright, let's finish this off. We've got a center of the circle at -1, +1, and a radius equal to the square root of 2. Okay. Well, now we've got some of these completing the square problems to look at. So, problem 6, we've got x squared plus y squared plus 4x plus 2y minus 20 equals 0. Okay. Now, how you handle this process is really up to you, okay? There are a lot of different ways to go about doing this. I like to move any constant pieces, anything that's not a variable, just move it to the other side, get it out of the way, okay? You can leave it around if you want to. And then I group the variables. So I'm going to have the x's, and then I leave a space for completing the square, and then the y's with a space next to it so I can complete the square there. Okay. So now we're all set up, right? Remember the process. Look at this coefficient here. Cut it in half to know what to put in the parentheses, and then square it to know what to add to both sides. Okay? We'll do the same thing here. Look at this coefficient, cut it in half to know what to put in the parentheses, and then square what's in the parentheses to know what to add to both sides. So, what we end up with, there's the standard form of the equation, and then I think we need the, center and radius. So, our center is going to be -2, -1, and our radius will be equal to 5. All right. So I think that's an excellent problem to get us started with this process of completing the square. Let's move through a couple of these, and then we'll look at some trickier problems where we have to complete the square. All right. Problem 8. X squared plus y squared minus 6x plus 2y plus 9 equals 0. Okay, so I'm going to do the same thing. Let's move this over to the other side and then collect our variables with room to complete the square. All right, so I'm going to cut this in half to know what goes in the parentheses. Now square this so that we can know what to add to both sides. And we'll do the same thing for the y's. Cut this in half, we get a 1, and then square it and add it to both sides. And there's our standard equation. So our center is going to be the point 3, -1, and then our radius should just be equal to 1, right? Because these 9's are going to make 0, and so we'll just be left with that 1. Okay. Well, let's see here. All right, let's look at problem 12. Okay, so problem 12, 2x squared plus 8x plus 2y squared equals 0. And so again, the real key is that the coefficients in front of the squared pieces have to be the same to make this a circle. And so let's go ahead and divide everything by that 2. So this will be x squared plus 4x. Let me leave a space here. Plus y squared still equal to 0. Okay, so we need to cut that 4 in half, make it a 2, and then square it so that we know what to add to both sides. And over here, the y squared just stays the way that it is, and there's the standard form for this circle, with a center at -2, 0, and then the radius is equal to 2, right? The y coordinate for that center is 0, because y squared is the same as y minus 0 squared. All right. Let's keep going with these. Now we start to get into the ones that are a little bit tricky. Problem 14. And they're not even really that bad. It's just, you might need a calculator to figure some of these values out. Plus x plus y minus a half equals 0. Okay. So I'm going to do the same thing that I always do. I'm going to move the constant piece to the other side. And then I'm going to collect the x's and collect the y's and leave a space to complete the square. All right, so here's where it gets a little bit tricky. The coefficient for the x here is 1. So if we cut it in half, this is going to be x plus a half squared. So now what we need to complete the square, what we have to add to both sides is going to be 1/2 times 1/2, which is 1/4. And you can do this with decimals if you prefer. There's no reason why you have to use a fraction in this problem. In some other problems you might run into repeating decimals, which get a little bit messy, but you can still work with those too. And the y is going to be the same. This is going to be y plus a half as well. And we're going to have to add another 4th on. So these are all going to add up to 1. There's our standard equation. The center is at the point -1/2, -1/2, and our radius is equal to 1. Okay. That's problem 14. I guess we'll just do the rest of these. Problem 16 is next. So, problem 16, 3x squared, 3y squared, minus 6x plus 3y equal to 4. Okay, so first thing I'm going to do here is divide out these 3's, okay? So we've got to divide everything through by 3's. So this will be x squared plus y squared minus 2x plus 1y equals 4/3. And again, if you want to call that 1.3 repeating, at least make sure that you know that this is a repeating 3 and not a terminating 3. It's a big difference. Okay, so now let's group our variables and leave space to complete the square. Okay. So, cut the 2 in half. This will be x minus 1 all squared. And then we'll have to add 1 to both sides to complete that square. The coefficient here is 1. So, cut that in half. And then we'll have a half inside the parentheses. And then to complete the square, we'll need a 4th on both sides. So this idea of completing the square is kind of interesting. And this is something that the Mesopotamians did geometrically, where you've got something where you've got like, you know, x plus 2, and then x plus 2, okay, and then you get this shape that looks something like this. You've got an x squared, a 2x, a 2x. Oh, let me make these solid lines. And then the piece that's missing is this piece right here, is that 4. So that's why I always say I need this piece to complete the square. Geometrically, what's happening is that you actually are completing a big square. Okay? All right. So let's finish off this problem here. So now, this is what I was talking about before. You're going to have to add 4/3 plus 1 plus a 4th. So what? This is 16 twelfths, 12 twelfths, and 3 twelfths. That's 28/31 over 12. Again, if you prefer decimals, at least, you know, just use the bar to indicate a repeating decimal. Don't round it off or just truncate it. 2.583 repeating. 583 repeating. Nothing wrong with that. That's fine. All right. Now, where's the center of the circle? Center of the circle is where x is 1 and y is -1/2. And the radius, we don't have to get fancy with this. We can call it square root 31 over 12, which is the same as square root of 2.583 repeating. And if we want a good approximation for it, you can do that as well. You know, just take the square root, about 1.61. But if you do that, it's always good to put those curly equals to, because that indicates to people this is a rounded value. This is not an exact value. It's been rounded. Okay? And these straight equal signs indicate that these are exact values. I get into this sometimes. I can't remember which topic it is. I think it's in Math 111, one of the topics we do, where I ask them for both the exact value and also an approximated value. Because as I say, well, it's nice to know that this is an exact value, but exactly what is it, right? So this gives you an idea for what the number actually is, whereas this one holds all of the accuracy, but it doesn't really tell you where the number is. Okay, so that's problem 16. We got 2 more to look at. Let's go ahead and do those. All right, problem 18. Let's see what we've got here. So we start out 2x squared, 2y squared, minus 5x plus y equal to 0. Okay? So we'll go through and we just have to divide everything by 2. So these cancel and we'll get x squared plus y squared. You can keep it as 5 over 2 or you can call it 2.5. And here, again, you can call it 0.5 or you can call it 1/2 y. Either way. Now let's separate our variables and put in a space so we can complete the square. There we go. Okay, so I'm going to switch to fractions so I don't have to use the calculator. So this is 5 over 2, and this one is 1 over 2. Okay, so if we cut this in half, that's going to be 5 over 4 squared, and then to complete the square, we'll need 25 over 16. Add that on both sides, right? If I kept that in decimals, this would have been 1.25, and then I was kind of hesitant. I just didn't want to bother with the calculator to square 1.25, okay? If you've got the calculator in front of you, it's not an issue, okay? But try not to round, right? Let me take the time to talk about this a little bit. In some situations, it's not going to make a difference, in others it will. So this 25 over 16 is 1.5625. Now, a lot of students I see have this aversion to any decimals that go past one or two places, and they just drop the rest of the digits. If your decimal is not repeating and it's less than 8 or 9 decimal places, there's no reason to drop this extra accuracy. There's no reason to get rid of it. Okay? So hold on to that. You may find significant situations where your accuracy is really affected by those decimal places. There's a classic story when they were first using GPS. There was an error in one of those satellites that was in the 10th decimal place. That's 10 to the minus 10. Well, on the ground, that was a difference of 50 miles. Okay? So, it's important to know how the accuracy of your decimal is going to affect where it's used in an application. There's actually a whole area, one of my professors when I was in grad school was talking about this whole area of mathematics that is about how your rounding affects your accuracy. Okay? So anyway, enough about that. Let's go ahead and finish off problem 18. So this is going to be y plus a fourth all squared, and then to complete that square, we're going to need 1/4 squared, which is 1/16. So it looks like we're going to come out of this with 26 over 16. So the center of the circle is going to be the point 5/4, negative 1/4, and our radius is going to be the square root of, well, let's go ahead and reduce that, because that's bad form. If we just leave that as 26 over 16, that's going to be 13/8. 13/8. So, and that's the square root of just 1.625. So let's get an approximation for that. What do we get? About 1.27 as the radius. Okay. That's problem 18. And I really think that it's helpful to work these problems that have non-whole numbers in them, okay? It's very, very typical when you're working in applications to have these, strings of decimals that you have to carry around and calculate accurately with. And so it's a good thing to practice so that you can do it competently. Okay, minus 7x plus y equals 0. And one of the things that is really useful in doing that is on the graphing calculator, this button down here, the STO key, will store values. So like if I had a long decimal, it was at 1.5625. Now if I wanted to do something with that, and I didn't want to type it in all the time, hit that type in number, hit the STO with the arrow on it, and then you'll see a little arrow on the screen, and then store that as X. Type the X key and hit enter. Now you can just use X, and anytime you hit X, it'll record that as 1.5625 until you change the value of X. Okay, let's do problem 20. Let's see, we got to divide everything through by 2 here. So, x squared plus y squared minus 7/2 x plus 1/2 y equal to 0. Alright, so this is going to be x squared minus 7/2 x, leave a space. Y squared plus 1/2 y, leave a space. 0 on the other side. Okay, so we got to take this coefficient and cut it in half, and that'll be 7/4. Then we got to add 49 over 16 to both sides to complete that square. All right, here, cut that 1/2 in half. That'll be 1/4. Square it to complete the square, and we get 50 over 16, which is 25 over 8, or 3.125. All right, so our center of our circle is going to be the point positive 7/4, negative 1/4, and our radius is going to be the square root of 3.125. And let's get a good approximation for that. See what that radius is. 1.77 is, I think, pretty good approximation. Okay, so that's it for section 2.1. That's about all we're going to do with the circles. The next couple sections we're going to look at are going to have to do with parabolas, and we're going to leave aside the ellipses and the hyperbolas in the interest of time. They work in a very similar way that the circles and the parabolas do. If you run into applications where you need those other conic sections, I think the material that we cover on the circles and the parabolas will be helpful for you if you ever work with ellipses or hyperbolas. Okay, as always, if you have any questions, please let me know. Thanks.